Welcome to the first video for our last SLO of the semester, SLO 11, where we'll be talking about the chemistry of amines. So to get started in this conversation, I think it would actually help us to think more broadly than just amines as a functional group and think about nitrogen in general. So this is a really important element for a variety of reasons. It comes up constantly in the chemistry of life. So in biochemistry, you'll be thinking about nitrogen all the time. But it turns out that nitrogen's properties change a lot depending on the kinds of structures it's involved with. And that's a truism in the sense that, that's true for all atoms. But it seems that nitrogen is even more susceptible to influence from neighboring groups or even atoms to which it's attached than pretty much anything else. And part of that has to do with the fact that nitrogen on its own is kind of right on the knife edge of a variety of properties, right? So if we think about nitrogen, there's a couple of things we'll notice. It's kind of electronegative. So our electronegativity is, let's just say it's equal to 3.0 out of a 4-point scale. So fluorine has got an electronegativity of 4. Oxygen's around 3.5. Chlorine is also just about 3. This is where the foncal versus focal ne comes from. So really, nitrogen is a little bit more electronegative than carbon, but not dramatically so. We also know that we're going to typically have 3 bonds and 1 lone pair. And that will be a typical bonding pattern, but we've seen lots of other possibilities, right? So there's like 4 bonds and no lone pairs. Which would make your nitrogen positively charged. And we've also seen situations where we could make nitrogen negatively charged. So 2 bonds and 2 lone pairs is going to give us a formal negative. And nitrogen, pretty much unlike any other element that, we would think about as organic chemists or really biochemists, can actually be neutral, positively charged, or negatively charged. And those structures would actually make sense, that you could actually access things that are at least somewhat stable in all 3 of these charge states. We can't do that with oxygen. Lots of neutral oxygens, lots of negatively charged oxygens, but very difficult to make positively charged oxygens. They definitely exist, but these are typically highly reactive compounds. The same thing with carbon. Neutral carbons, all over the place, right? But positively charged carbons, generally a problem. These carbocations exist again, but they're reactive intermediates. And negatively charged carbons, with a couple of exceptions, right? So we've seen some highly stabilized enolates, things like that. Normally these negatively charged carbons aren't stable either. So nitrogen's kind of unique in that all of these charge states and bonding patterns are commonly found. So nitrogen supports all these. And that's really a consequence of its electronegativity, right? 3 is essentially electronegative enough that negative charge can be supported. It may not be a great negative charge, but we're, getting to the point where that's reasonable. It's not so electronegative that you couldn't support positive charge, and it's certainly fine for supporting the stability of a single lone pair. But in the neutral state, so neutral nitrogens, these are typically going to be sites of reactivity, although we'll see some important exceptions where this isn't true. So these will be centers of reactivity. Often these will be bases and nucleophiles because of this lone pair. Right, we've got this lone pair that's relatively unstable. So remember, it's not that the lone pair is totally destabilized. It's not a carbene ion, for instance, right? But it's also, this lone pair is a lot less stable than one on an oxygen atom because of this electronegativity difference, right? And so we see these neutral nitrogen functional groups as very important for the chemistry of life and also for the chemistry that humans do. because of the fact that we can make subtle changes to these structures, change charges, change lone pair stabilities, and we can move around in this kind of knife edge of reactivity where we can access basicity or nucleophilicity, or we could make things that are positively charged for whatever reason we might want, right? Maybe we're thinking about making salts or disinfectants. These are the quaternary ammonium salts that people have been writing about with respect to like hand sanitizer. Or even using things that are negatively charged for our various purposes. So the purpose of this first video really is to get us thinking structurally about the kinds of concepts that we've encountered this semester, and some from last semester as well, that we will actually use to explain how nitrogen differs among different kinds of nitrogen functional groups. So in the next section of this video, we'll actually look at some of those specific kinds of functional groups and work to classify as well as analyze their structures. We'll look at 4 major classes of nitrogen-containing functional groups. Sometimes people call all of these structures amines, but that's really misleading because their structures vary in sometimes pretty obvious ways, but more than anything else, their function changes quite a bit depending on structure. So we'll start with what an amine, with an N as in Nancy or November, actually is. This is a nitrogen with 3 bonds and a lone pair. That nitrogen needs to be sp2 hybridized. And that means that it's going to have a geometry that's not flat. So it's probably not tetrahedral. It's probably some kind of a distorted tetrahedron. So some people like to call this like, a trigonal pyramidal geometry or something like that. So we'll say this is distorted tetrahedron. So I've tried to depict that in my drawing here, right? So we can have a variety of different kinds of groups attached to the nitrogen. Those R groups could be alkyls or other kinds of carbon groups, or they can be hydrogens. If we make R's other kinds of what are called hetero atoms, so for instance like an oxygen or another nitrogen or a chlorine, we actually start changing the functional group so much in terms of its, function, that we give them different names. So really we would think about R as being equal to carbon that's sp2 hybridized, so this would be like an alkyl chain, or hydrogen. Those are going to kind of be our options for R groups. And they can all be the same, they can all be different, and we can talk about substitution pattern with respect to the amine by counting the number of hydrogens. So our substitution of the amine is going to be the number of H's. Actually, the easiest way to do this is the number of carbons on, or attached to N, so like directly attached, is the degree of substitution. So, for example, if we looked at methylamine, the lone pair of nitrogen. Remember, it's not trigonal planar, even though we actually would typically draw the structure this way. We would think about the nitrogen being kind of the tip of a point. We've got 1 carbon directly attached to the nitrogen, so this would be a primary amine. On the other hand, if we looked at, let's say, diethylamine, lone pair, again, not planar, we would have 2 carbons directly attached to the nitrogen, so this would be a secondary amine. So you'll note that even though there's 4 carbons in the substance, I'm only looking at the 2 carbons that are actually directly attached to the nitrogen to work this out. And then a tertiary amine, or a 3rd degree amine, please don't say 3rd degree, it's tertiary, would be 3 different carbon groups. So we've learned about these throughout the semester, like for instance triethylamine, so 3 carbons directly attached to nitrogen. Okay, so these amines, they tend to be fairly basic. We'll look at some properties. Fairly basic at nitrogen. So we know that their conjugate acids are ammonium ions. So for instance, if we took maybe our primary amine, methylamine here, and reacted this with a proton. So we're using the structure as a base now. That the nitrogen lone pair, because it's not that stabilized, is going to be reasonably basic. There's some kind of driving force to make a new bond to this nitrogen. So this would be our conjugate acid. This is my ammonium ion. We call this the methyl ammonium ion. And it's got a pKa of, well, you should know this still, about 10. Okay, so these primary amines, or sorry, these amines are also nucleophiles. They're fairly nucleophilic at nitrogen. For the same reason that we saw they were somewhat basic, right? The lone pair is kind of stable. So these aren't the world's best nucleophiles, but they're certainly better than, say, most neutral oxygen atoms, right? So amines are kind of the vanilla case for nitrogen in the sense that these are kind of the simplest structures. The least amount of work goes into analyzing them. We're basically just working with the electronegativity of nitrogen. Of course, other factors that we thought of before, like induction, are going to make a difference here. But our crucial idea is that we can consider both the basicity and the nucleophilicity of the nitrogen, and really any other atom we wanted, by using the structural tools that we've developed, right? The more stabilized the lone pair gets, the less reactive we are as bases and nucleophiles. So analyze lone pair stability to assess reactivity. So this is an idea that you've seen multiple times throughout the semester, but we're seeing it here as well. So there's one other feature, though, especially with amines, that we do need to consider that's not directly related to lone pair stability, and that's actually sterics. So as we actually start to add more groups around the nitrogen that are bigger than a hydrogen atom, the nitrogen gets blocked out, right? There's a lot of things that get in the way of serving these roles. So we could say that amines, and especially amine nucleophilicity, is sensitive to sterics. So let's look at an example of this. Let's take our methylamine. So our methylamine here has this one methyl group and then two hydrogens. So if this nitrogen is nucleophilic, as it approaches an electrophile, the methyl group could get in the way. These hydrogens are very small, and we know that the nitrogen is actually kind of the pointy end of a spear in the sense that this nitrogen is not flat. And so that actually makes this nitrogen fairly nucleophilic. But let's actually now consider the same case where we add another methyl group. So we're going from a primary amine to a secondary amine. So we'll look at dimethylamine. All right, so we still have essentially the same amount of lone pair stabilization here. You could make the argument that these methyl groups are, inductive donors or something like that. Some people like to make this argument. These are not strong effects, really, in most cases. So the secondary amine here, really the way these two differ is in sterics, right? Two methyl groups is quite a bit larger than just one. And this effect of sterics, of essentially part of a reactant site nearby getting in the way, physically blocking the electrophile and the nucleophile from coming together, that's what's going to dominate these reactivity differences when we're talking about differences in degrees or different substitution patterns for amines. So these are similar in lone pair stability, but different in sterics. And what we can conclude here is that for simple amines, there's going to be a strong correlation between the substitution, or the degree, and the nucleophilicity. Less substituted nitrogens is more nucleophilic. So this idea in green is just a consequence of our analysis in red, right? Typically we focus primarily on how stable the electrons are that are making up the nucleophilic site. But here, because those differences in electron stability are very small, the steric difference will dominate. And that actually is pretty common for amines. So we could even take this out to like a tertiary amine, and we find that they are nucleophilic, but much less so than a secondary or a primary amine. And in fact, this is why we were using triethylamine as a base way back in SLO5 when we were learning about acid chloride reactions and things like that. So tertiary amines are much less nucleophilic, but you'll notice that the basicity of these amines changes just only a little bit when you go from a primary to a secondary to a tertiary amine. Usually you're talking about pKa differences for conjugate acids of like 1 unit, right? So you're not talking about big differences here. So this last thing that I wanted to note is that even though nucleophilicity is strongly impacted by sterics, basicity is not. So primary, secondary, and tertiary amines differ only slightly in basicity. And so from this we can conclude is that sterics don't matter much for base strength. Like I said, there are some differences in basicity between primary, secondary, and tertiary amines. I'm not going to hold you accountable for knowing those trends because, in part, they're highly solvent dependent. So if you look at pKa data measured in different solvents, you can get different kinds of trends. So what we'll really focus on is this distinction where nucleophilicity of the amines highly impacted by sterics, and that's going to be controlled essentially by substitution pattern. Whereas basicity, we're looking at very minor effects in terms of how strong these nitrogen bases are. So we'll turn our attention next to another kind of nitrogen. So rather than amines, we'll look at a different nitrogen type. We'll look at amides with a D as in dog. So amides, or amides, depending on how you like to pronounce this, notably with a D instead of an N, are very similar to amines. We've talked about amides a few times during the semester. There's essentially, the big point of difference is the carbonyl that's directly attached to the nitrogen that we're analyzing in this particular case. So because of this, we know that the nitrogen itself is sp2 hybridized. So N is sp2, and therefore it's trigonal planar. You might be a little confused about why the nitrogen is sp2 hybridized if you think about hybridization as essentially a counting game where I have 1, 2, 3, 4 things that are on the nitrogen. But hybridization, remember, correlates just with geometry. And for this nitrogen lone pair to be delocalized or conjugated, the nitrogen needs to have a p orbital. And that means that the nitrogen needs to be trigonal planar in order to have that p orbital. So we can talk about amides or amides in terms of resonance, which we saw back in SLO5. And we talked about these in the context of nitrogen being a resonance donor to the carbonyl. Well, that same idea applies, but in this SLO, we're just going to change our frame of reference, right? Rather than analyzing what's happening at the carbonyl, or at least the carbonyl-carbon, we're going to be analyzing what's going on at nitrogen, and especially the carbon-nitrogen bond. So we know that this lone pair is delocalized. I'm showing that here just to tie this back to the hybridization. If these two structures both exist simultaneously, this nitrogen needs to be able to form a pi bond, which means it needs to be sp2 hybridized. So that's one of these differences between an amide and an amine is the hybridization of nitrogen. We also know that this nitrogen is delocalized, or the lone pair is delocalized, and that tells us a few things. This delocalization is stabilizing to the lone pair, And so we would expect, one, for the nitrogen to be less basic than an amine. And resonance effects are usually fairly powerful, so let's say that it's going to be much less basic than an amine nitrogen, and it's going to be much less nucleophilic. All in the consequence, again, of structural analysis, where we're focusing on lone pair stability. In fact, this effect of the lone pair on nitrogen being delocalized is so significant that what we normally find is that the amide structure itself, it's not even nucleophilic or basic at nitrogen anymore. It's actually nucleophilic and basic at oxygen. So amides with a D are basic and nucleophilic at oxygen. And I think this minor resonance structure tells us why. This lone pair exists heavily on an oxygen, and if we mix together the charges that we get from the minor resonance structure with the neutral form that we usually would draw, we find that really it's the oxygen that's unusually electron rich. It's going to have a partial negative charge, and nitrogen is actually kind of electron poor. It's going to have a partial positive charge. This is essentially a consequence of this delocalization, right? So the relative strength of nucleophilicity and basicity of these amides, pretty weak. So this idea about being much less basic or much less nucleophilic than amine nitrogens, absolutely true, but it's like both weaker and at oxygen instead of nitrogen. So there's one other thing that I wanted to point out here, and that's that if we think about a resonance hybrid, we would need to draw kind of partial pi bonds between the carbon and the oxygen and the carbon and the nitrogen. And I'm not going to put any lone pairs in because I don't know where they go. And I'll put my partial charges in. The carbon-nitrogen bond here has partial pi bond character. And this is an important consequence for biochemistry. That means that the nitrogen-carbon bond is unusually stiff. It's very hard to rotate. So very difficult to rotate. Because if I actually rotated the carbon-nitrogen bond, basically what would happen is I would start where those two atoms are aligned, their p orbitals are aligned like this, right? Remember the pi overlap is side-on rather than head-on, so like this. And what happens is I start to rotate the C and the N bond is that pi bond actually breaks because I'm actually rotating the p orbitals out of the bonding arrangement. So to actually rotate the carbon-nitrogen bond of an amide, you have to break this partial pi bond character. And that basically makes it so that these bonds are fairly rigid. They don't really rotate. In fact, you'll typically see this in most biochemistry textbooks. You'll read things like, the amide bond is rigid. And then often not really an explanation for why, but it's well within your grasp. This is an effect of resonance and the fact that these nitrogens are good resonance donors to the oxygen. So why is this important? Because proteins, as you probably have already learned, are made up of an amide backbone. So we're repeating units of amide linkages, and the reason that you can have these kind of semi-stable secondary and tertiary structures for proteins are because those backbone amides can kind of lock in place, right? So you can lower active rotation barriers and stuff, and there are enzymes that do that. But really, once you make the protein and you fold it appropriately, it kind of stays that way, more or less. And that's important. If the bonds were freely rotating, like most single bonds are, proteins wouldn't have any defined structure, and that means they probably wouldn't really have any defined function. So you could make the argument that it's this partial pi bond character in amides, because of what we know about resonance and nitrogen, that really gives rise to life. Nitrogen's pretty important. So this is going to mean stable protein structures. I'm using stable kind of colloquially here, right? As you'll learn in biochemistry, and maybe you've already learned in other classes, it's not that these protein structures are totally fixed. They do have some ability to be manipulated and move, but these are much more rigid than you would think about for like another molecule of its size that maybe just had carbon-carbon bonds, for instance. Okay, so we've done our analysis of an amide, right? So key takeaways are hybridization difference, right? Lone pair on nitrogen is far more stabilized than an amine, and that gives rise to a consequence of very weak reactivity, and that reactivity showing up at oxygen rather than nitrogen. And then finally, this notion of this partial to high bond character being important for the structure of amides, and that's important for biochemistry. So next we'll look at what happens when we change this carbon-oxygen double bond into some other kind of a pi bond system. So rather than an amide, we'll look at other kinds of conjugated nitrogen groups. Another kind of conjugated nitrogen group is called an aniline. And these are typically going to describe an amine that's actually attached to an aromatic ring. So a kind of working definition of an aniline is an amine group in which at least one R group is an aromatic ring. So these anilines have a great deal of historical importance for organic chemistry. The birth of organic chemistry as a discipline basically comes from the chemistry of anilines, because these compounds, once they start to react, can become highly colored. And so the synthetic dye industry, which, you know, all of our clothing is colored with synthetic dyes now, all comes from aniline chemistry, and we actually get aniline from coal tar. So this was starting in Germany and in the UK in the 1850s. So it's kind of the birth of organic chemistry, where at that point it was kind of like, well, we mix these random things like coal together and we get purple. Well, that's cool. And then all of what we've been doing for the last 160 years or so has been, well, why do these things happen? What else would be true about molecules, right? So really you could think, you know, the idea, the human desire to have colors in our lives for organic chemistry. So these anilines are easy to spot for this idea. And the same visual cue that we're using to identify an aniline that have this benzene ring attached to the nitrogen is also going to dictate the reactivity of these nitrogen groups. Because we know that the benzene ring is a weak resonance acceptor for the aniline nitrogen's lone pair. So we could talk about nitrogen donating its lone pair into the benzene ring. And if it does that by resonance, which it would have to, then we have a set of resonance structures that would look, clean this up a little bit, like that. And we could actually move the negative charge like around the ring. So there's a set of resonance structures that describes the lone pair from nitrogen and where it ends up, or rather where it exists. So like that as well. So if we look at these resonance structures that we've drawn, this one and this one, there's a problem in that I'm placing a negative charge on carbon. And that means that these structures independently are probably not very stable. And that also tells us that these are going to be very minor contributors to the overall hybrid of an aniline. So these are going to be very minor, certainly more minor than the resonance structures we looked at for amides in the previous section of the video. But they still exist. And that tells us a few things. One, the nitrogen is still going to be sp2 hybridized. So because nitrogen is a pi or resonance donor to the benzene ring, N is sp2 hybridized and therefore planar, trigonal planar. Remember, anytime I'm invoking an atom like a nitrogen as a resonance donor, it has to have a p orbital to do that, and that requires it to not be sp3. That also means that the nitrogen lone pair is going to be somewhat more stabilized. Again, relative to an amine. Let's say an unconjugated amine. And that means that aniline nitrogens are going to be both less nucleophilic and less basic than unconjugated amine nitrogens. So aniline less nuke and less basic than unconjugated amines. Okay, you'll notice that I'm not making a comparison to amides yet, although we will do that in a couple of seconds here. One thing I do want to point out though, unlike amides, it's still going to be the nitrogen that's the reactive site here. Because these are such minor resonance structures, most of the electron density from this lone pair is on nitrogen. Like I'm going to make up some numbers, like 95% of it or something like that. The carbonyl would be different. It's a much better resonance acceptor, and so you have a lot more of the electron density on oxygen. So here, nitrogen is still our site of reactivity. Both for basicity and nucleophilicity. Okay, so we've kind of described these anilines in a similar framework that we've used countless times this semester. I'm kind of hoping that you're like, yeah, I get it. I see it's conjugated. I understand the consequences. And if that's the case, then awesome. I do want to show you a little bit of data so we can get some kind of quantification for these ideas that the nitrogen lone pair being a little bit more stable is going to make it a little bit less reactive. And I think the easiest thing for us to do is actually look at acid-base chemistry. So we'll do this for aniline itself. This is the simple molecule that I started with. Although anilines as a class of structures would have this and other junk other places in the structure. And we'll just look at what happens when we react this with just a proton. So we're just going to look at the conjugate acid here. All right, so we've got our proton. We'll draw our conjugate acid, which has a fun name. The nitrogen becomes tetrahedral, right? Because there's no longer a lone pair to donate, the nitrogen is going to have 4 bonds and it's not tetrahedral, so sp3n, tetrahedral. This is called, well, we usually take the name, drop the vowel at the end, and add IUM for a positive charge. So this is an anilinium ion. Anilinium ion. So this is a conjugate acid of aniline. And it has a pKa of about 5. So when we compare that to like an unconjugated amine, those have pKa's for their conjugate acids, ammonium ions, of around 10. So we can see that this aniline is a weaker base than the amines. All right, and we can also compare this to amides. So we'll look at a very simple one. Excuse me. So if we reacted this compound with an acid, we would need to draw the conjugate acid. And like I said, we actually end up protonating the oxygen. So this would be the conjugate acid of an amide. This has a pKa of around 0. So what we've concluded here is that between the nitrogens of amines, the nitrogens of anilines, and the nitrogens of amides, the amines are the most reactive, both in terms of basicity and nucleophilicity. The anilines come in between because I'm doing a little bit of resonance donation to the benzene ring, and amides are the least reactive because I'm doing a lot of resonance donation from the nitrogen to the carbonyl. Okay, so we have one more kind of nitrogen group to look at, and we'll do that soon. The final kind of amine or nitrogen that I would like to discuss is a little bit more of a potpourri or a grab bag. And there's not really any great term for all of these kinds of structures, so I've essentially made one up. I'm going to call these heteroaromatic amines. So you won't find this language in your textbook. You won't find this language on the MCAT, but I think what you will find is that this kind of classification is actually quite helpful for as you learn about similar structures in biochemistry and you see them across different kinds of applications. So I'm showing you 4 examples of heteroaromatic amines, and you probably notice a few things here. One is they all have nitrogens. Shocker. The other is that all of these structures have aromatic rings in them. So the 6-membered ring in the structure we call pyridine. In pyrrole, it's the 2 double bonds and the lone pair on the nitrogen that are the aromatic system. On imidazole, there's 2 double bonds, and then again the lone pair on one of the nitrogens is part of the aromatic system. In an indole, we have 2 different aromatic rings, like a benzene ring like we're used to. And then a double bond, another double bond, and a lone pair. All of that goes up to make an aromatic system. So a working definition for this concept of a heteroaromatic amine would be a nitrogen that is actually a part of an aromatic ring. Actually, let me choose my words carefully. Rather than system, I want to say ring, like I said, but didn't write. So a couple of notes here. Depending on the exact structure, the nitrogen's lone pair may be a part of the aromatic system. So you think back to like Huckel's rule, so the 4n+2, that kind of a system. So nitrogen lone pair may or may not be a part of aromatic system. So that's like the 4n+2. Whether or not the lone pair is a part of the aromatic system will dominate its function. Okay, so let's actually look at this concept on all of our example structures because words don't really help as much as looking at a few examples. So let's look at pyridine first. Well, let's work left to right. So the nitrogen is definitely one of the members of the ring, and so we would say that pyridine is definitely heteroaromatic amine. But if we wanted to know about something about its reactivity, we would need to analyze the lone pair specifically. And to do this, we're going to try to decide, is this lone pair localized, or is it actually a part of the conjugated system? There's a few ways you can do this. I think the easiest way is to try to draw resonance structures. So you could try to do donation like this, but if I did that, remember there is a hydrogen here, I'll go over the octet rule. I'll end up with 5 bonds between nitrogen and carbon, so that can't work. Well, maybe I'll just go the other direction. We still have a problem though. We also have a hydrogen here, and so that would give us 1, 2, 3, 4, 5 bonds. That doesn't work either. So this lone pair is actually not a part of the aromatic system, even though the nitrogen is a part of the ring. So nitrogen lone pair is localized. And as a consequence, we could look at conjugate acid pKa's. We've used those as a guide to discuss relative reactivities earlier in this video. So the pKa, so if I put a proton on the nitrogen become positively charged, is about 5. So this is kind of similar to an aniline. For different reasons, remember this nitrogen is localized. So we don't have this kind of resonance argument anymore. Instead, we would need to talk about the hybridization. So nitrogen being sp2 hybridized stabilizes the lone pair relative to being sp3 hybridized. And that's where we get this kind of decrease in reactivity, in this case basicity, relative to like a normal amine where the nitrogen is sp3 hybridized. Okay, so let's look at the pyrrole case. So I'm going to try the same thing. Can I donate the lone pair? All right, well, I could try to do that, but now I'm going to have 5 bonds, except for I can keep going. So it looks like I can delocalize the nitrogen lone pair in pyrrole. Right, so the lone pair is a part of the aromatic system. And in fact, that's how I would say that pyrrole is aromatic. If we applied the 4n+2 rule, we've got 2 pi electrons from this double bond, 2 pi electrons from this double bond, and the lone pair electrons are part of that cyclic pi system. So we have 6. And we can make 6 equal to this if n is 1. So we need that lone pair for pyrrole to actually be aromatic, and it is. So let's look at the pKa here. But before I give you the number, I bet we could make some kind of qualitative determination. So if that lone pair is a part of the aromatic system, it should be highly, highly, highly stabilized. This is like the extra special magic version of conjugation. So it's really powerful, much more powerful than we would normally even think about resonance. And that means that removing the lone pair by protonating the nitrogen would actually destroy aromaticity for the entire ring. That sounds horrible. Like, why would the lone pair ever be involved in that? And that's true. If we actually look at like the acidity of the compound that lost its aromaticity, it's really, really acidic. So this is equal to -2, right? So one way we could interpret that is that losing the proton to get the lone pair back to become aromatic, awesome, huge driving force to do this, all right? So our lone pair that is part of the aromatic system is highly stabilized. Much more so than any of the other kinds of nitrogen lone pairs we'll talk about in this video. This aromaticity is like a huge effect relative to anything else. Okay, so let's keep working. So we'll look at the imidazole now. Now we've got 2 different nitrogens to analyze, but we'll do them one at a time. So we could keep using this resonance drawing rule, and that's always going to work, but you have to draw resonance structures, and I know how much you love to do that. So, although I think it's good practice. We could also try to draw patterns from pyrrole and impurity. So one of the things that I notice is that this nitrogen is a part of a pi bond already, and it also has a lone pair, which apparently can't be involved in the pi system. This nitrogen doesn't have a pi bond right now. So it's a lone pair. If it's donated, the nitrogen gets a single pi bond, right, in the resonance structure. And that actually works out for us, is that N with a double bond rarely donates its lone pair. And nitrogen without a double bond, depending on the neighbors, can. Okay, so if that's true, we see this top part in purity and this bottom part in pyrrole. So no double bond here. I do have a conjugated system, so that lone pair can be delocalized. So let's apply these to imidazole. So if I look at this nitrogen here, it looks a lot like a pyrrole nitrogen. So this nitrogen, no double bonds to it, its lone pair is going to be able to delocalize, right? I have this conjugated system. And so we could say that this lone pair is a part of the aromatic system. And then we could look at the other nitrogen. So this nitrogen is participating in a double bond. And if we did this resonance test, we would find that we could not delocalize this lone pair. So this is actually pretty common, that depending on the specific environment of a nitrogen within an aromatic system, the nitrogen may or may not have this kind of aromatic stabilization for its lone pair. So we could make a few different decisions here. One is that of the two nitrogens in imidazole, one is more reactive than the other. So this nitrogen is more reactive. And this is a pretty significant difference. Right? You could call this nitrogen pyridine-like, and this nitrogen would be more pyrrole-like. And that's actually pretty close to true. If you look at the conjugate acid pKa's for the two nitrogens, this nitrogen will be around 7, and this one will be around 0. So we can see this kind of pattern that's playing out. What I'd like for you to do then is look at indole and use what we've developed, either the resonance test or these other kind of rules. I want you to make a prediction about the pKca for indole. So that would be the case where this nitrogen had no lone pair, another hydrogen, and a positive charge on N. All right? So pause your video and make a prediction of the pKca for indole now. So you've had a chance to think this over and hope that you probably try to use both of these tools. Right? You first try to draw some resonance structure, see where that gets you, and then you can double check your work using these kind of shortcuts. Remember, don't just apply the shortcut rules. You're not learning anything by doing that because you will forget these. Whereas being able to draw resonance structures, as you've seen all semester long, is a skill that gets applied in all sorts of different problems, and that will be true in biochemistry. You'll still be dealing with resonance in biochemistry. You will not be dealing with this rule. So let's see if we can delocalize this lone pair. If I donate it here, I'm going to go over the octet rule, but I have the option now to go further, and it looks like I should be able to donate the lone pair. So that looks good. I'll be able to draw a valid resonance structure. I could also apply my rule in green. So this nitrogen, as drawn, has no double bonds, and the nitrogen is part of a conjugated system, so I should be able to see delocalization. Both of those suggest the indole nitrogen is a lot like the pyrrole nitrogen. So nitrogen lone pair is a part of the aromatic system. Highly stabilized. And our pKca, hopefully you said 0 or less than 0. It's also about -2, very similar to pyrrole. Okay, so we've gone through a few different examples where we're not only deciding that these are all heteroaromatic amines, we're kind of distinguishing them into these two classes where the nitrogen lone pair can either be delocalized into the aromatic system or is actually localized itself. So notably, the ones that are delocalized into the aromatic system are essentially not reactive. They're so stabilized that they're essentially not nucleophilic sites and they're not basic sites. On the other hand, the nitrogens that are localized, like this one or this one, those are weakly reactive. These are often very similar to anilines in their reactivity, both in terms of basicity and nucleophilicity. Okay, so in the last section of this video, we'll look at a couple of other problems where we just classify, kind of work through some complex structures and describe each nitrogen in them as different kinds of amines. So let's look at 3 different biologically important amines. So we have adenine, right? This is essentially the nitrogenous part of adenosine, one of our nucleobases. Serotonin, so a neurotransmitter, and penicillin, which is an important antibiotic. So we've got lots of nitrogens, and it's going to be helpful for us to be able to classify them quickly because we know that the classifications correlate with reactivity in some sense. So if we look at adenine, we could start anywhere. I'm going to choose this nitrogen to begin. So I'm going to ask myself a few questions. I'm going to ask about hybridization, conjugation, and aromaticity. So this nitrogen here looks like the nitrogen is conjugated, so it's next to a carbon that's got a p orbital, right? So this nitrogen will be sp2. And that means that this cannot be an amine, N, like November. It looks to me like there are aromatic rings in this molecule. So one of them is the 6-membered ring here and the 5-membered ring here. These are both kind of aromatic. And so that tells me that this could be an aniline. I'm not entirely sure yet. It's definitely not an amide. There's no carbonyl. And so what I need to decide, is this an aniline or is this a heteroaromatic amine? And to do that, make that decision, I'm going to decide, is this nitrogen actually a part of the ring? And the answer is no. So this nitrogen is an aniline. Okay, so one way you can do this is process of elimination. So we'll just work counterclockwise around the ring now. So for this nitrogen, I'm going to play the same game. So this nitrogen is sp2 hybridized, so not an amine. There's no carbonyl, so not an amide. And it is in the aromatic ring, so it's a heteroaromatic amine. Okay, so this nitrogen looks very similar to this one. Okay, so also heteroaromatic. All right, well, this nitrogen looks different now, so we'll do the analysis again. It would be tempting to say that this nitrogen is sp3 hybridized, but this lone pair is delocalized, like we talked about in the previous section of the video, and that means this nitrogen requires a p orbital. This nitrogen is a part of the conjugated system. So we know that this nitrogen at the bottom, here on the bottom right, is sp2. So it's not an amine with an N. It's not an amide because there's no carbonyl. And now we need to decide, is it an aniline or is it a heteroaromatic amine? So it's a part of the ring. It's in the ring. So again, it's not an aniline. It is heteroaromatic amine. It differs from these two nitrogens, which I've labeled in green, because the lone pair on this nitrogen is a part of the aromatic system. It's extremely stabilized. These two nitrogens, their lone pairs are localized, right? They're not a part of the aromatic system electronically. And so these lone pairs are somewhat reactive, right? So these are kind of, in the pKa5 kind of regime. So even though they're both heteroaromatic, they're a little different. If you like the nomenclature, you could call these pyridine-like, and this would be pyrrole-like. Okay, so one more nitrogen to go. So this one here, this looks a little bit like imidazole from the last video. It's kind of like an imidazole ring. So not an amine, it's sp2 hybridized. Not an amide, no carbonyl. It's a part of the ring, so it's not an aniline. And it's kind of like a pyridine type. The lone pair is localized, so this would also be heteroaromatic. I'm just going to circle it. The green goes with this label here. Okay, so we can also look at serotonin. Here are just two nitrogens. So this nitrogen looks a lot like this one. The lone pair here is a part of the conjugated system, right? So it's sp2 hybridized. The lone pair is a part of the aromatic system. So this nitrogen is a heteroaromatic amine, the nitrogen in the ring. So here's my heteroaromatic. And the other nitrogen's way out here, so lone pair. Okay, so here, this nitrogen is not conjugated. This carbon is sp3, right? This nitrogen would have no reason to retain a p orbital for conjugation. And so this is an amine with an N, right? So as soon as we find sp3 hybridization, there's only one thing we can do. Okay, so finally we'll look at penicillin. So we've got, let's see, two different nitrogens here. So we'll start with the one on the left. So this one here. Hybridization, it looks like I should be able to delocalize my lone pair into this, oh wait, carbonyl. So this looks like an amide. And as we know from previous SLOs, we could call this a secondary amide because I've got 2 non-hydrogen groups. And then we could also look at the nitrogen that's actually part of the 4-membered ring, which is kind of weird. But it's okay. We don't have to worry about the fact that it looks a little different. We can apply the same techniques we've been using. So I'm going to see if I can delocalize this. I can, into the carbonyl. So it looks to me like this is not an amine, no N, right? I'm going to be sp2 hybridized. And it looks like there is a carbonyl, and so this is an amide. It's different from this amide in a couple of ways. One, it has 1, 2, 3 non-hydrogen substituents, so this is a tertiary amide. The other thing that I notice is that it's a part of a ring. So this 4-membered ring here, the nitrogen is a part of that ring. Be careful, right? Just being a part of the ring does not make you heteroaromatic. The ring needs to be aromatic itself for this to apply. So we would instead call this sometimes a lactam, which would mean a cyclic amide. So this concept of lactam, it's just enrichment. I'm not going to hold you accountable for that, but you may hear the term like lactam antibiotics, or beta-lactamase is an enzyme that gives rise to resistance to penicillins, and that's what they're describing, is this 4-membered ring, this lactam, sometimes called a beta-lactam, to describe how the ring is formed. That's the mechanism of action of this drug involves this carbonyl acting as an electrophile, and that it actually ends up killing bacteria through that function. The lactam is critical. So you might run into this word lactam if you're interested in antibiotics, or if you're interested in synthetic materials, so like nylon fibers are all synthesized from lactams. So remember, lactams just cyclic amides. So we've gone through a system for identifying different kinds of nitrogens, and that's helped us to correlate reactivity. So we'll then go back through these structures now very quickly to find the most, or maybe the least in some cases, reactive nitrogen. So here I've got a bunch of different heteroaromatic nitrogens. Without doing a detailed resonance analysis, I don't know which of them is the most reactive, but they're all going to be much more nucleophilic and basic than this nitrogen, right? This nitrogen that's heteroaromatic, where the lone pair is a part of the aromatic system, is going to be the least reactive nitrogen in the structure. It's very likely that this aniline nitrogen is going to be the most reactive, right? Both for steric reasons, as well as the fact that that this lone pair, even though it's delocalized, right, this hybridization effect that impacts other heteroaromatic species tends to be a little bit more important, right? But it's kind of a close call. What we could definitely say with adenine is that this nitrogen definitely far less reactive than any of the other 4. In serotonin, again, no contest, right? This nitrogen here, which is kind of a part of an indole ring, yeah, basically not a reactive site. So I shouldn't have said basically. Not basically. It's not anything. It's basically, dang, I did it again, just going along for the ride. This amine is far more nucleophilic, far more basic than this nitrogen is. So any type of acids are going to react here. Any kind of electrophiles are going to react out here. Penicillin, we've got 2 amides that are quite similar. And so if all we had was the tools we've developed over the course of this video, and also from previous parts of the semester, we would think of these 2 amides as being very similar in reactivity. Both oxygens could be protonated. We know the carbonyls are a little bit electrophilic, and the nitrogens themselves are probably not going to be the sites of reactivity directly. If you're very interested in how lactam antibiotics work, it's worth knowing about the beta-lactam and how that's kind of a special version of an amide. So if you're curious, you can look that up. There's a good Wikipedia page, or we can talk about it by email or in office hours.